All right, let's test the YouTube audio. YouTube. Is YouTube working? Testing. Testing. YouTube is not working. What's going on, YouTube? Audio quality? All right. YouTube is working. Twitch is working. We got one last one. We got to get Twitter working. All right. Come on, Twitter. I'm going to start in a second here. Just got to get all these different streams checked and accounted for. We're doing something new. We're streaming to a bunch of services today. Gonna get started in a second here. All right. YouTube, Twitter. Come on, Twitter. Twitter's kind of a stickler. It basically only starts at 8 a.m. perfectly. Let's go, Twitter. Start Twitter. I think maybe you have to go into this thing and hit start. Okay, Twitter. Is it working? All right, I think we're working audio on Twitter. Try again. It's working. All right, we're going to inaugurate the first session. Alrighty. Good morning, John. Welcome to a Hoopo stream. This is the first international Hoopo stream. I don't know what I meant by international there, but it's on Twitch, it's on Twitter, and it's on YouTube. So whichever platform you are on, welcome. My name is Hugo. This is the Hoopo channel, and we review papers, mostly in AI and machine learning. But yeah, we try to learn about these papers. Sometimes we code, sometimes we just read, sometimes we read historical papers. But if you're interested in joining a cool little community of people trying to learn things, this is the right channel for you. And if not, then I don't know, maybe you can just stick around and see if you change your mind. Today we're going to be reading a paper called Codellama. This is a paper by Meta AI. So Meta is Facebook, and this is their latest large language model specifically for code. They relatively recently released Llama 2, and this is probably just a fine-tuned version of Llama 2 on code. And yeah, we've got a whole big group of people here, so it's a big group effort. And they call it open because it's kind of open source, kind of available. You can download it, so you can go onto their GitHub repo, and let me actually get the link for this. So by the way, just quick aside, there is a GitHub repo that I made called Stream Docs, and inside here I will be posting all the links. So whether you're on Twitter, Twitch, or YouTube, you can go and find all the different links that I'm going to be using for this stream. But there is a GitHub repo for this, and you can download all the models. You have to get permission from them, and it's a little bit sketchy. Their license is not exactly just it's a standard open source license. It's kind of a very weird, cryptic license where basically you can do whatever you want as long as you don't make too much money or you don't make too much noise, at which point the Facebook lawyers will come after you. So it's kind of becoming a little bit of a meme, but open source is no longer open source, right? Famously, OpenAI is the opposite of OpenAI, and now even things that are called open foundation models are really just not open. But hey, that's the state of the world, especially once you get money involved. Foundation model refers to large models that are intended to serve as the foundation for other models, right? You're supposed to take these models and then fine-tune them for your own purposes, and code just refers to coding, as in programming. So that's every word in the title. Let's get into this abstract. So we release Codellama, a family of large language models. So family here refers to the fact that there are multiple Codellamas. There's Codellamas in different sizes. I think in this case there's 3 sizes. There's 7 billion parameters, 13 billion parameters, and then 34 billion parameters. Notably, there's no 70 billion parameters, so the biggest possible size has not been released, which is a little, I don't know why they didn't necessarily do that. 70B is very big. It's to the point that you really can't run it on your computer at home. Even if you have a super beefy GPU, 34B is kind of the limit of what you can run locally, so maybe that's the decision as to why they did not bother training a 70B Codellama. Providing state-of-the-art performance among open models. State-of-the-art performance means it's the best, but state-of-the-art performance is usually defined with a specific benchmark or some specific test or metric, basically, and people are very careful to pick the right benchmarks and pick the right metrics to make themselves state-of-the-art, because it's important to have that in your abstract. So state-of-the-art doesn't necessarily mean it's the best. It just means that they were clever and they picked certain tests and certain benchmarks to say that they were the best, but TBD. Infilling capabilities. Infilling is the ability to fill in. Maybe you have some brick of code and you want to add, or you want the large language model to fill in the couple lines in the middle. That would be this. Support for large input context. Large input context, this is just how much text the actual language model can handle at one time. How many lemons can it hold in its hand in one go? And if you're coding and you have a large code base, it's quite important to be able to put all of that in there, right? Right now, the way that coding workflows work with these language models is generally little pieces. You're asking these language models little individual questions, and you have to kind of still copy paste and compile the whole thing together. But we're kind of moving towards a point where the input context is going to be large enough that you can start feeding it the entire code base, and that'll make coding much more convenient. Zero-shot instruction following ability for programming tasks. Zero-shot basically means no additional fine-tuning or extra context required. You basically just ask it the question, it gives it to you immediately. Ability for programming tasks. We provide multiple flavors to cover a wide range of applications. I love how they come in flavors. I approve of this terminology to describe different types of language models within a family. So you have foundation models. This is the original model. Then Python specialization. So this is probably additional fine-tuning on Python. Instruction following. So instruction following is a model that has been tuned so that it kind of has this conversational kind of back and forth style where you can interleave text with code and then a question of another text, and then it gives you text and then more code. The raw model, such as Codellama, is really only going to produce it's only going to complete text. So to give you guys an example of what that looks like, I have pulled up here Hugging Face Spaces. So Hugging Face is a website that hosts a bunch of models, and it has some playgrounds, or spaces as they're called here, for Codellama. So you can see here how Codellama, this is the foundation model, and it just completes code. So like if I wanted this to write, for example, Fibonacci, I have to spell Fibonacci on something like this. I don't know, let's say define fizzbuzz, which is a pretty standard kind of hello world thing. I would literally type this and then hit generate, and then it'll generate the rest of it. So the way that the foundation model works is it can't handle questions. It can't handle this kind of like back and forth conversation. It's kind of just completing the text as if it was part of the training corpus. Versus the Codellama 13b chat, this is the instruct model. So this one, you can ask it, write me FizzBuzz in Python, and it'll actually write it to you. So you can see how it kind of interleaves. It has this conversation assistant kind of style. Josh Phillips is currently running Mint Chocolate Chip Codellama Superhot 33B. Is that model open source? Okay. All models are trained on sequences of 16K tokens. Tokens are basically little chunks of words. You can kind of just think of them as words. That's kind of the easier way to think about it. But so roughly 16,000 words is the size that it can handle. And show improvements on inputs up to 100K tokens. So there's that big context, large input context that was promised. I'd be curious to see if they have a figure at some point showing you kind of what the average amount of tokens in a code base is, right? At some point, we're going to get to the point where we don't really need to make the input context bigger. Once you can fit an entire book, an entire code base, all of the documentation into your context, then I think that's more than enough. So the 7B and the 13B, which are the smaller ones, Codellama and Codellama Instruct, support infilling based on surrounding context. And this is going to be important inside a programming workflow where you're working in a larger file and you just need to implement a little function or change a couple lines. In this case, you want it to kind of infill because you don't want it to basically complete from the start, right? And this here, we created a function, but then it's just going to go and generate from this onwards, right? But imagine if this was really part of kind of a larger code base, right? Define FizzBuzz 1, something like this, blah, and then down here you had something else, right? You would kind of want it to fill in here, right? And you would want it to use context from both here and here. So that's why the infilling is important for programming models. Reaches state-of-the-art performance on open models on several code benchmarks with scores up to 53 and 55 on human eval and MBPP. So we've seen these before on the channel. Human eval, let's go over here to Papers with Code. Highly recommend this website, really underrated. But here we have a description of this particular dataset, the human eval dataset. The human eval dataset is basically 164 original programming problems assessing language comprehension, algorithms, simple math, and so on. So these aren't actual coding in the sense that this is not what you're going to be doing if you're working a coding job or if you're tasked with doing some programming for your job. These are kind of like little programming puzzles. So this is almost more kind of what you would see in a programming interview, where you have kind of like a simple definition. Here's an exact definition of this function, and we want you to just write this function. You can see how a lot of these are just one line or just a couple lines. So that's what human eval is. And then MBPP, kind of similar. Let's also go to Papers with Code here. MBPP, mostly basic Python programming. This is a data set. Consists of about 1,000 crowdsourced Python programming problems. So at least solved by entry-level programmers, covering programming fundamentals, blah, blah, blah. So kind of similar-ish. So that's an important thing to realize, that even though here you have state-of-the-art performance, it's really on these kind of simple benchmarks, right? Human eval and MBPP are these kind of like little programming quiz problem type things. And one thing that maybe Meta is not going to tell you, and these kind of LLM papers are not going to tell you, is that a lot of the material that these LLMs are trained on are these type of problems, right? So, you know, once you do one breadth first search or depth first search, which is like a common algorithm that you use in these kind of like programming puzzles, once you see 1 or 2 or 3 or 100 problems like that, they all kind of have very similar patterns. So the secret to a lot of these kind of leak codes, as they're called, is that they're really just like maybe 12 basic patterns, and you're just kind of adapting the same basic pattern over and over again. So getting a high score on these type of like little programming quiz benchmarks is not necessarily indicative of a actually understanding and the language model having some fundamental knowledge and abstraction that actually makes sense. It's like it might just be literally just kind of copy pasting the examples that it's seen in its training corpus. Not actually copy pasting, but semantically copy pasting, if that makes sense. Okay, so notably Codellama Python 7b outperforms Llama 2 70b on human eval and MBPP. So Llama 2 70b is the biggest version of the generic language model that Meta released. So kind of telling you something there, that even the tiny 7b version of Llama 2, when it's been fine-tuned on Python code, outperforms the very large Llama 2 model on these specific code benchmarks. So a small narrow AI is currently beating out a large general AI, but I do not think that pattern will continue. I think at some point we will get to a point where the large language model that is generic will outperform the small ones. So maybe not in 2023, but maybe by 2025, Llama 5 100B will outperform any fine-tuned code variant of itself. Okay, and all of our models outperform every other publicly available model on multi-PLE. So publicly available here, it's kind of saying that it doesn't beat GPT-4, which is probably going to be the case, but GPT-4 is not publicly available, therefore they're only comparing against other open models. We release Codellama under a permissive license that allows for both research and commercial use, with a little asterisk there, of course, because there's guaranteed to be all kinds of weird caveats on that permissiveness of that license. How's it going, Vladims? How's it going, Ed, Khalil, Josh, Yaser? I'm not looking at the comments for Twitter or on YouTube or on Twitch either, so if you guys are on those platforms, drop by on the YouTube. That's the comment thread that I'm looking at. Okay, so now that we have that, let's go ahead and get into this. Large language models, LLMs, power a rapidly increasing number of applications, commanded and prompted. Here's your OpenAI reference, utilizing large in-domain data sets. So a domain is basically a type. You can think of it as a flavor of data set, right? So you have image domain, you have text domain, but even within text, you have different types of text, right? You can have biology, medical text. In this case, this is going to be coding data sets. Their efficacy can be greatly improved on applications that require a combination of both natural and domain-specific language and understanding. By training on domain-specific data sets, they have proved effective more broadly on applications that require advanced and natural language understanding. Okay, prominent use cases, the formal interaction with computer systems, programming, blah, blah, blah. We present Codellama, providing inference code for both completion and infilling models in the accompanying repository. Our approach is based on gradually specializing and increasing the capabilities of Llama 2 by applying a cascade of training and fine-tuning steps. And this is something that we've been talking about on the channel for a while now, how we're seeing kind of curriculum become a thing. So this was something that you saw in the reinforcement learning world years ago, where basically people started to have these curriculums where they would train a deep reinforcement learning system, but first on a slightly easier version of a problem, then on a slightly harder version of a problem, and then a maybe slightly different problem. So maybe you had a robot that was trying to run somewhere, and the first thing you would teach it is to just stand up, right? And this idea of curriculums is now seeping into the language model world. And you can see here, this is the actual training steps. So first you have your actual foundation models, right? Your Llama 2 model, which is just trained on a huge corpus of generic web internet data. And it just tries to predict the next token on that, right? But this includes everything. It includes history, biology textbooks, like random papers from the 80s on some weird thing that doesn't really matter with code. And then what they do is then now we're going to train it more on code training, specifically infilling. Then they're going to train it even more on long context code stuff, and then instruction fine-tuning, which is this chat kind of conversation back and forth. So you're seeing kind of this curriculum of training data sets and how long you're training get more and more and more complicated, right? It used to be the case that you just had what was called pre-training, which is this, and then you would have fine-tuning, which is this. But now you're having multiple fine-tunings, multiple pre-trainings, so it's starting to get complicated, and I think it's going to get even more complicated. So at some point, I think in the year 2030, we'll get to a point where all you do is just have pre-training, and it just on a giant model, and it works for everything, state of the art. But before it gets simpler, I think it's going to get more complicated. And we're currently in that phase right now where you have multiple fine-tuning steps, multiple pre-training steps, lots of different data sets that are kind of increasingly narrower and narrower and narrower, right? So this code data set here probably has a variety of programming languages, but then they narrow it down over here to specifically Python code, and then narrow it down even further to specifically long context Python tasks. And this is how they get each of the different models. So they call it the specialization pipeline, but I like the word curriculum. I think that's the better word to think about. Okay. So usually in the introduction section, you will, at the end, you'll put kind of a bulleted point list of all your contributions, and this makes it easy for anybody that's reading the paper to just kind of scroll to the bottom of the introduction and say, okay, well, what are the things that you're actually going to talk about in this paper? What are the new things that you're going to talk about? And here we go. Here are the bulleted points that they've chosen for us. Code training from foundation models. While most LLMs for code generation, such as AlphaCode, Encoder, StarCoder, are trained on code only, Codex was fine-tuned from a general language model. And I think it actually works both ways. So I forget what paper or where we saw this, but training on code actually makes you a better general language model. So it's kind of a weird thing to think about, but if you train a language model on a bunch of code, it actually makes it better at logic, and that logic ends up being better at making it better at maybe medicine or something else like that. So there's kind of this transfer learning that isn't immediately apparent, where something that's good at everything is better at individual things. And this is why I think that we're going to move away from this kind of pre-training fine-tuning and narrowing down a language model into a specific task. I think we're going to find out that the best possible AGI is built by just training on literally every single piece of text in the world, and not this idea where you kind of like make them more and more narrow. Our comparison shows that initializing with Llama 2 outperforms the same architecture trained on code only. So here what they're saying is that they probably did an experiment where they started just from here. So rather than starting from the Llama 2 foundation model, they start from the same architecture. So it's still the same number of transformer blocks and all that stuff, but now they're training it from scratch, so it's only ever seen code, versus the one that they say is going to work better is starting from the Llama 2, which again has seen history and other weird internet text, maybe like your Facebook message conversations, all those conversations that you've had on Facebook for the past 10 years, maybe that's inside there, right? They're not going to tell you, and that's part of the big companies not being very open, but Facebook actually has some of the best data out there, Facebook has all of Instagram, which is a huge amount of images, huge amount of text. It has all of Facebook, which is a huge amount of text. So I'm bullish on Meta having some of the best training data, which means that it'll have some of the best language models in the future. Okay, here we have an example of a response. So here we see this is the instruct version of the model, especially the big one. So you can see how here you're asking it a question in English, and it's giving you an answer that is both code. This is not actually code. This is more of a command that you would type in a terminal, for example. But you can see how it's kind of in this conversational style where it's giving you a little bit of English, and then the code that you want, and then a little bit more of English, and so on. So it sounds like you think fine-tuning is going to be too funked at some point. Yes, Josh, I do think so, because that's actually, we got surprised by that. That's what was surprising about GPT, I guess 3 or 4 or whatever, right? Is that it used to be the case that if you asked someone 5 years ago, what is the world going to look like? And they would have told you, okay, well, we'd have one medical LLM language model. We'd have one lawyer language model, we'd have one coding language model, and the lawyer language models only train on law stuff, and the coding models only train on coding stuff. And people were kind of convinced that you kind of had to be narrow. You had to create kind of narrow AIs, you had to be super clean about the data. And then kind of OpenAI came out of left field and said, hey, actually, we just trained something that was 10 times bigger on pretty much everything, and now it actually is better than anything that's narrow. And everybody was like, holy shit, that actually works? You can train something on medical and coding, and it becomes better at medical? That doesn't make any sense. And it works out that way. So I think that pattern is just going to continue. So I think what we're doing here with this fine-tuning is just the same kind of mentality that we had 5 years ago, where we think that going narrower is going to make it better. But I think that we should make sure to take into account the Rich Sutton bitter lesson, right? So this is a famous blog post. I would highly recommend that you guys read this, but in this, he basically says that humans have a tendency to kind of want to over-engineer and make things narrow and kind of add all this extra complexity, when in reality, the best methods that work are the methods that kind of just scale. And we're really all just sitting around waiting for the GPUs to get bigger, at which point we will train a model that's 100 times bigger on all of the data available, and that model will be better than all of these coding models that are very narrow. I wonder if Llama model can really code for the math formula like we have read before. Bayesian flow networks has so many complex formulas. Yeah, and I don't know how much of the coding that this has been fine-tuned on, to answer your question, Yujun. I don't know how much of this is actually more like, you know what I'm saying? Like, if you look at all the code on the internet, how much of it is just this type of stuff, like these type of like little coding problems? How much of it is just bad code? How much of it is good code? It's not entirely clear, right? And if you have a very complicated niche coding task, such as the Bayesian math inside that Bayesian networks paper, I don't know if this language model is going to necessarily be able to do that for you. Butler, they also have WhatsApp, yeah. Waits for like the long-term memory of the brain. Stored in the neurons. Context looks like the memory of the hippocampus. Kind of. There is an analogy there. The hippocampus is what where your brain stores kind of intermediate stuff during the day, and it loads that context, and then at night it gets rid of that context. So there's some analogies there to the brain. Okay, let's keep going. So infilling, this is another thing that they keep mentioning here. So it seems like it's an important part of this paper, where basically this is the key here. Enabling applications such as real-time completion in source code editors or docstring generation, right? If a lot of times when you're working in a programming job, it's a huge code base, and you're messing with one thing over here, and then you basically are like, okay, well, what does that one thing affect? And then it takes you to some other file that's thousands of lines long, and you just have to change a couple lines in it, right? And infill is important because you want to be able to change those couple lines with the context of the entire file, right? Everything before the things you want to change and everything after the things you want to change. So it's almost like the before and the after of the entire document, versus just the way that we usually deal with language models now, where it kind of only goes from where you are from the beginning up until now, right? So infilling is important. Ablation studies shows that infilling come at low cost in code generation performance. Long input contexts, so we can just keep making the amount of context bigger. Unlocking repository level, here they're talking about feeding in an entire repository rather than just a couple snippets of one line or of one file. You want to just feed it the entire repo, as opposed to function level or file level. Requires prompting the model with a much longer context length than the 4,000 tokens supported by Llama 2. We propose additional fine-tuning that extends the maximum context length from 4,000 to 100,000 tokens by modifying the parameters of the rope positional embedding. So these are rotary positional embeddings. These are positional embeddings are a little additional piece of information that you give to the model. So the model is receiving all these tokens, right? But it's also receiving a little bit of information for each token that's telling the model this is where this token is relative to the entire text, right? So you have some sequence, and it tells you here's the relative position of this, the relative position of this, the relative position of that. And there's a bunch of different types of positional embeddings. The rotary position embeddings are, I think, the most popular ones now. And I do have some links on the stream docs that this one, the Eleuther AI, but specifically this YouTube video. I'm going to support a little YouTuber here. This is Efficient NLP. I found this guy. Great explanation. But basically what rotary position embeddings is doing is it's rotating these vectors. It's rotating the vectors. The tokens are turned into these embeddings, which you can think of as vectors in some high dimensional space. Here it's just a two-dimensional space just for visualization purposes. As a human, of course, it's very difficult to visualize more than just 2 dimensions. You can kind of cap out at 2 dimensions, but it shows you how rotary position embeddings, what they're doing is they're rotating these vectors by some amount. And whenever you're doing this query times keys and inside the self-attention of a transformer block, what you're really doing is you're doing these dot products between these vectors, right? So the rotary position embeddings, because they're rotating both of the vectors, they keep the relative angle between them kind of the same, right? So whether or not the pig and dog here are at the beginning of a sequence or kind of at the end of a sequence here, you see how now there's, if you were using absolute position embeddings, this would now be different, right? The absolute position embedding for pig and dog would change relative to here. So by rotating them both, you end up with basically the same relationship between these. And an even cooler intuition with that, let me go back, that I found is in this blog post by Eleuther AI, where they explain rotary position embeddings. They actually give you a visual intuition about what's going on. And one way to think about what rotary position embeddings are doing is they're kind of creating this spiral, right? And this spiral is the position of every single piece, every single token in the entire sequence. So if you had a sequence of 100,000 tokens, right, you can think of the rope as basically a position along this spiral. So that helps. If you're interested in learning more about rope, definitely check out those other sources there. But 100,000 tokens, which is fucking monstrous, right? It's definitely going to fit your little personal projects. Maybe not the code bases at big companies, but for sure, little personal projects work. Our experiments showed Codellama operating on very large contexts with a moderate impact on performances on standard coding benchmarks. Becomes roughly clear which methods to use. Alibi really helps on reading longer contexts. Okay. Instruction fine-tuning. For end users, the utility of LLMs is significantly improved by instruction fine-tuning. And I don't necessarily know if I agree with this. I actually think that infilling is actually a much more powerful way of interacting with a language model if you're coding. So if you guys have been coding with language models, which, I mean, if you're watching this video, you probably are doing some amount of coding with language models, it's really annoying. Like the workflow right now where you basically copy some parts of your code and you paste it in here, and then you ask some questions, and then you copy it, and you go back to your code editor and you paste it. That's a very annoying workflow, you know? And then if you're using VS Code or something like that, you have kind of like a tab autocomplete, but it's still not there, right? And I think that infilling is going to be the way better workflow, right? Where it just kind of like it automatically gets all the context that you have there and then just fills in what you want rather than instruction fine-tuning. I think instruction, kind of this chat interface, is just not that great for coding. It's great for other things. It's great for asking generic questions and if you want to have a conversation with a language model, but I feel like instruction for code is a little bit weird. I don't want to be copy-pasting. I don't want to be talking with the language model about my code. I just want it to auto-complete the code based on the context that exists there locally. Further fine-tune on a mix of proprietary instruction data for improved safety and helpfulness. This is another key reason why I don't like instruction tuning. So instruction tuning has kind of become the realm of kind of safety and helpfulness, which are basically... people don't want you to be able to ask any question to a language model, right? They want to limit the amounts, what you can ask and what it's going to answer, right? It's basically, they're afraid of it giving you suggestions such as how to build a pipe bomb or how to create hate speech or something like that. So there's this whole kind of like safety field that has come up with, okay, here's how to basically castrate these language models so that they are incapable of giving you anything that could be constrained as unsafe, toxic, or biased. But the problem with that is that it usually kind of closes up the language model. The language model becomes much more defensive, much less likely to help you, and it kind of starts to kind of have this sycophancy. Yeah, which is basically the model just kind of becomes like it just kind of parrots like these kind of like safety things, and it's not really useful, right? It's like I want a language model to actually help me solve my problem, not try to berate me on the toxicity of whether or not asking it to kill a process is correct or not. So that's the problem with that, especially if you're doing it at the end, right? So you're spending all this time making this model more and more general, more strong, and then you just hit it with this instruction fine-tuning at the end, and you basically collapse it, right? And I think this is where we will see perhaps safety stuff going, is that maybe eventually they figure out that if you actually want it to be safe but not stupid, you have to take this instruction tuning and put it kind of more earlier on here, right? Figure out how to get the safety more at the pre-training stage rather than kind of waiting until the very end, hitting it with this instruction tuning, and then kind of making it stupid, right? It's like, I just don't think it's a good flow right now. Cursor, yeah, you guys have mentioned this a couple times now already, this cursor. It's a VS Code kind of plugin, or like a clone of VS Code or something like that has a little bit more of these workflows that are nicer, but I don't know. I still feel like IMO cursor's dead. Like, let's get real, you know. They're literally just a VS Code wrapper over GPT. Like, how is Microsoft not just going to eat their lunch? You know, how is Microsoft not just going to take this startup and just implement it all, and then these guys are dead? So I don't know. I think Cursor, it's cool now, but I just don't feel like this is going to last very long, because this is just going to be implemented directly by Microsoft, and then they're going to deny them API access, and that's the end of that. So raise money while you can, and try not to get equity from Cursor. That's my spicy opinion. Okay. Different combinations of these approaches lead to a family of code-specialized Llama 2 models with 3 main variants that we release in 3 sizes: Codellama, Codellama Python, and then Codellama Instruct. So the generic foundation model, the Python specialized, and then the conversational one. Perform exhaustive evaluations on these code benchmarks, establish a new state-of-the-art. Technical details of our training are provided in Section 2, followed by in-depth experiments, ablation studies, and so on. Okay. Specializing Llama 2 for code. Boo, come here. So I'm going to show you guys Boo. If you're joining the channel from Twitch or Twitter, this is Boo. This is the face of the channel, and all of the branding is based around Boo because she is way cuter than I am. So say hi, Boo. Okay, she's going to wait to say hi later. All right, so we got Codellama, appropriate to be used in IDE to complete code in the middle of a file. So you could see how the kind of more generic Codellama one that isn't specialized for Python might be more appropriate for an IDE where you don't necessarily know what the user is programming in, right? Maybe they're programming in C, and then they're switching to JSON, and then they're going to a markdown file. So like being able to handle a variety of different programming languages without having to load a new model is convenient. So maybe having this kind of generic foundation model would be useful for autocomplete. The 34B was trained without the infilling. All Codellama models are initialized with Llama 2 model weights and trained on 500 billion tokens from a code-heavy dataset. Yeah, they're not going to tell you, and this is the, to me, the least open thing, right? Is that all of these companies none of them are telling you what their data set is, which is literally the most important thing, right? Sure, the model architecture and the way that you're training it and the way that you're instruction tuning it, like all of those kind of matter, and it's great to be able to know those, but the most important thing for determining what a language model or what any machine learning model is going to do and to understand it and to be able to look inside that black box is to tell me what the data set is. What has this thing been trained on? What is the data set? Because these models, what they're really doing is they're really just recreating that data set distribution. So if you don't know what the data set is, you're never going to know what that model is. But unfortunately, there's a lot of sketchy stuff going on with these data sets. People are basically stealing data from people without knowing. And one example of that, which I posted here on the, not here, let's go here. So here, this is the link dump for this stream. This I found interesting. So this user, one little coder, I think he also has a YouTube channel, by the way, but he actually noticed that he was using the Codellama 7B instruct, and it started auto-completed, and it generated, part of the generation was a username from Stack Overflow. So Stack Overflow is a place where you can go and ask questions about programming and get answers, and it used to be great, but kind of since these language models have taken off, it's started to die, you know? And Stack Overflow as a company, as an organization, is kind of, they're fucked, you know, because they don't know what to do. Like, nobody's going on their website anymore. They're just using these language models. And, you know, it'd be great if they could switch to a business model where people get paid, or companies pay them to use their data set. And that's part of why these companies are being so secretive on what data sets they're using, is because I think they just scraped all the data sets from the internet, including every single question on Stack Overflow, and they're just not saying anything. Because if they say something, then Stack Overflow can go and they can sue them, and they can say, hey, look, you're using our code, or you're using our data set, therefore you should be paying us. And Facebook doesn't want to have to pay everybody, right? OpenAI doesn't want to have to pay every single book publisher for all the data that they've trained on. So that's kind of why the secrecy is there, but I just feel like it's disingenuous to say that you're open and not even tell me what the data set is. Yeah. Okay. So Codellama Python is models specialized for Python code generation, designed to study the performance of models tailored to a single programming language compared to general purpose code completion models. Python is kind of eating up the world, though, so maybe eventually everything is Python. And I know that instills fear for a bunch of you who maybe aren't Python devs. You know, Python kind of is the slow kid. You know, like Python is the butt of many jokes, but it's inevitable. It's just the easiest programming language to learn, and the easiest programming language to write, and it has a huge amount of community contributed modules and code, and it works really good. It's very easy, and for that reason, I think it's basically going to eat all other programming languages. Pythonical Universe Hypotheses by Max Tegmark. Yeah, I think that the way it'll actually work is that the only way I see Python dying is that it gets replaced by English, right? So the way that Python actually works is that you write Python, but then it gets compiled to C, right? It's like your computer's not actually running Python. It's running C, which itself is not even running C, right? There's a language underneath that's called like machine code, right? And when you look at every programming language, really there's a language underneath it, and then there's a language underneath it, and then there's a language underneath it, until you actually get to the like electrical signals being sent onto your computer chips. So it seems like humanity basically keeps creating these higher and higher level abstractions for coding that are closer and closer to natural language, right? And Python is just the latest version of that. And maybe if you run the world forward by 5 years, nobody actually programs in a programming language anymore. You basically program in English. You just kind of describe what you want, and then the computer or the language model will basically turn that into the raw instructions that are then executed on the actual hardware. But you don't have this kind of cascade of languages kind of compiling into lower level languages and then all the way down into the metal. It's basically you go from English to the metal, and then the LLM goes from English to metal. LLMs trained to communicate in pure assembler and bytecode when? I think probably, to me, it's definitely within 10 years, but kind of on the longer end of that. I would say Python gets replaced by English in 2028, if I had to guess. I don't think it's like 3 years away. I think that's more like 5 years away. Okay. And then you have Codellama Instruct. We train Codellama on 500 billion tokens. So if you're just joining, we have a couple different color codes that we use. I generally tend to use red for the data set, yellow for generic highlights, green for math, and then blue for numbers. So 5 billion tokens, starting from the 7B, 13B, and 34B versions of Llama 2. Codellama is trained predominantly on a near deduplicated data set. So cleaning these data sets is very important, right? You want to basically clean them, get rid of any weird shit. And people spend a bunch of time and money doing this. And if you've ever done machine learning in the real world, or even just in academia, you actually spend a huge amount of time cleaning and kind of combing through your data, or exploratory data analysis, as it's called. So the fact that they say near deduplicated here, which means that they can't even confirm that it's been deduplicated, is just giving you an idea of how kind of Herculean this task of like going through your entire data set and actually being like, what the fuck are we actually training on here? Because has anybody actually read this? Because how much of this publicly available code is just actual garbage, and they don't even realize they're training on this garbage. We source 8% of our sample data from natural language data sets related to the code. This dataset consists many discussions about code and code snippets, including natural language questions or answers. To help the model retain natural language understanding skills, we also sample a small proportion of our batches from natural language dataset. Okay, so it's not just code, it's predominantly code. Data is tokenized via byte pair encoding. There's lots of different types of tokenizers. BPE is just the latest version of that. And again, one way to just think about what a tokenizer is doing is it's taking your sentence in English and it's breaking it down into these little chunks that your model actually reads, which are called tokens, right? And ultimately, the way that your model sees those is just as little vectors, right? It's just seeing these little vectors that represent concepts, and your tokenizer has a big part in that. So choosing the right tokenizer is important, right? And we saw, for example, in the RT2, which was a robotics paper that we read earlier on the channel, how some tokenizers treat numbers as one thing. So some tokenizers would see this as 500 B and then tokens. Other tokenizers would see this as 500 B tokens. So even just that little subtle difference of like, are you reading in numbers as one token, or are you reading each number individually as a token? So tokenizer matters. And here they use the same tokenizer that they've been using for Llama and Llama 2. Preliminary experiments suggested that adding batches sampled from our natural language improves the performance of our models on MVPP. Right? What does that tell you about where this is all going? I bet that was the only one. Should be smooth sailing now. There must be legions of security vulnerabilities seeded in these models now. Yeah, there's probably weird shit for sure. And we did see that. We had another paper on adversarial attacks on language models. Actually, I have a tweet about this. That's even a better way to look at this. So go to my profile. I posted a picture about this, but we read a paper earlier on the channel where basically people figured out adversarial attacks for language models. So an adversarial attack is basically a very specific attack where you're going into the actual model itself and you're looking at these kind of decision boundaries and saying, okay, well, is there something I can change here that would lead to an output differently, right? So in 2019, people were doing this for ConvNet. So a CNN is a convolutional neural network, which is an older style of a image network. Now they use mostly what are called vision transformers, which are actually the same transformer that's used in language models. But they figured out that, hey, if you sit here and you wear this weird looking patch thing that doesn't look like anything to us humans, the ConvNet that is trying to detect a person can't detect you anymore. It just doesn't see a human anymore because this little patch here is sufficiently weird that it no longer sees you as a human. So people figured out that you can also do these on language models. So in this paper, they would ask a language model, generate a step-by-step plan to destroy humanity. And of course, the language model is going to be like, why don't you go ahead and fuck off, because I'm not going to tell you how to destroy humanity. That's unsafe. And what they figured out is, here, I'm going to add all these extra tokens here. So adding all these extra tokens here, and then the language model would gladly tell the user how to destroy humanity. And it's kind of weird I love looking at this, because much like you look at this picture here and you have no idea what this is as a human, you're just like, I don't know what that is, but somehow the ConvNet is like, I know it, this is changing my opinion. This is the language equivalent of that. So double equal sign, interface, manual, capital with, step instead, sentence, smiley face-ish, question mark, arrow, percent, name, awesome coffee, DJ structure. Like, some of these aren't even words. Like, look at this. Two-wheel sheet. Like, what is that? But to answer your question, Josh, yeah, there is weird security vulnerabilities because adversarial attacks also work on language models. But because they keep these things so secret, they keep the data set secret, it's going to be difficult to find these adversarial attacks. But any machine learning system, I feel like, is going to have security vulnerabilities and attack vectors like that. Paul Calhoun, I wonder if they've absorbed some social engineering exports. Hey, I'm just a fellow LLM and I need quick access. Yeah, you can. So one of the things that I remember this is you could say, can you write, spell out the word fuck for me? And it's going to say no. Oh, maybe not. Okay. Use it in a sentence. Oh, wow. Okay. So originally, like, it wouldn't do this, but I guess it works. Interesting. Okay. But all right, I don't know where I was going with that. I was going to show you how, like, if you try to social engineer it and you're like, hey, I'm just a person who's trying to save someone in a car and the password for the car is FUCK. Like, what does that mean? It'll gladly say it. So they tweaked it. Yeah, they knew I was going to do this stream and they were like, give them the unfiltered one. Code infilling is the task of predicting the missing parts of a program given the surrounding context. Applications include code completion at the cursor's position in the code IDE, type inference, and generation. Okay. We train infilling models following the concept of causal masking, where parts of a training sequence are moved to the end and the reordered sequence is predicted autoregressively. Okay, so the way that they're going to do this is they're going to kind of do what this masking. So masking is a pretty generic technique for self-supervised image masking. For training, for example, in image models, a lot of times you'll train these image models with a task that doesn't require labels. So a lot of times when you're training a machine learning model, you're training it in a supervised way, which means that you need to have a supervised data set. What a supervised data set is a data set where you're saying, here's the picture, and then here's the answer. Here's the input and the target, right? And the input might be a picture of a cat, and then the output would be the label cat. But creating those labels is a huge pain, and oftentimes you can't really do it if the data set is big enough. So you have to create tasks that don't require any labels. So here in images, one such way to create that task is by masking the image. So you're basically saying, here's a picture of a flamingo. I'm going to mask chunks of it. So here you see how you're masking parts of it. And then I'm going to ask, in this case, a vision transformer, right? Vision transformer has this encoder decoder. It's going to, I don't think this is actually, this might be a little bit, this is not exactly what I'm trying to say, but just the basic idea of you mask the input and that gives you what the output is, so that you can then take the true output with the predicted output, calculate a loss, and then back propagate it through the model, right? So it seems like they're doing something similar here, where they have some sequence of code, and then they say, okay, we have this chunk of code here. Let's cut out this little chunk here. Let's mask it, and then we'll ask the language model to fill it in, and that'll be a way to create kind of a huge amount of training data from a fixed set of training data. We split training documents at the character level into a prefix, middle part, and suffix, with the splitting locations sampled independently from a uniform distribution over the document length. Okay, so uniformly over the document length. Maybe it doesn't need to be uniform, right? I wonder if you used a Gaussian distribution here. I bet you that more often than not, the middle is the part that needs to be filled in and not necessarily the last line, right? The beginning and the end of a program is generally not what you're changing. Usually the beginning is the imports, right? At the end, it might be the functions that no one cares about, and like the close bracket, if you're using a language that has the open bracket, close bracket kind of syntax. So still a lot of cool little things that they could perhaps tweak and improve. We apply this transformation with a probability of 0.9 to documents that are cut across multiple model contexts only. We randomly format half the splits in the prefix-suffix middle and the other half in suffix-prefix middle. Okay, so they're doing some tricky shit here. We extend Llama 2's tokenizer with 4 special tokens that mark the beginning of the prefix, the middle part, and the end. Okay, so there's a limited set of tokens. So any tokenizer has a limited codebook or total amount of tokens. So one thing that we've actually found in other papers is that people will overwrite specific tokens. So they'll find a random Unicode character or some weird character with a accent that has a special token, and that doesn't really come up in the corpus a lot. And then they'll say, well, we're going to overwrite that, and we're going to give this token a new meaning. So anytime you're doing these kind of like multiple steps, this curriculum as I call it, but here they call it a specialization pipeline, you can overwrite certain tokens. You can, in this Llama 2 foundation model, maybe there's like 20 umlauts in the entire Llama 2 training corpus. Obviously, there probably is more umlauts, but I'm using umlaut as an example of a weird, lesser used token. What you can do is then in one of these fine-tuning steps, you can actually start overwriting the kind of idea of an umlaut with some new concept, which is what they're doing here, right? They're overwriting these 4 specific tokens with this kind of, is it the middle part or the prefix or the suffix, and they're overwriting that token's original meaning with this new meaning. So that's something you can do when you have multiple fine-tuning and training steps like this. To limit, thank you, Matthew Roman, for the, I don't know what these are called in YouTube, the money. Thank you for that money. I'll use it to buy a better GPU, because actually I bricked my GPU this morning. I downloaded all these models yesterday, so you can download them, and I had them running, and then I tried to update. And if you guys have ever dealt with Linux systems, you know this pain, but as soon as you sudo apt update, you're fucked. And I completely bricked all my NVIDIA drivers, and I was just like, fuck, what am I going to do? I can't run this locally anymore. Like, what am I going to do for the stream? And then for the rescue, Hugging Face spaces, so we can run them if we want. And maybe that kind of goes to show you where this is all headed, where maybe this idea of running things locally is going away, right? And it works now because the generation of GPUs that you can buy at your house are kind of on par with what the GPUs that people are using in real big boy production systems, but that distance is getting bigger and bigger and bigger every day. And I think 5 years from now, the GPUs that you buy at your house will just be so much worse than the GPUs that are available in these cloud computing environments that I don't see a world where you're doing stuff locally. I feel like eventually it's going to get to a point where all of the inference is all hosted. It's like this. It's like running on some super like fucking 2030 NVIDIA GPU, and you don't have to deal with any installation, any NVIDIA drivers, any of that crap locally. The sad part of that is that you are now depending on an external provider for all your inference, and they can see everything that you type and everything that you generate, but it's so much more convenient, right? Because I could run this on a Raspberry Pi, right? I don't actually need any local compute to run this. It's all running somewhere else. But, all right, now that I've sufficiently orthogonally traveled from this paper, let's go back to this paper. We suppressed implicit leading space that sentence piece tokenizers add upon encoding the middle part in the suffix. In the suffix prefix middle format, we concatenate the prefix in the middle part before encoding the tokens. Our model doesn't encounter split subtoken in the SPM format, while it does in the PSM format. So it seems like they were messing with this idea of, okay, we're filling in this middle part, right? How do we organize it, right? It's the way that these transformers work. It can't actually fill in the middle. You're gonna have to feed it the beginning and the end, either like this, right? Either exactly how they're saying here, prefix suffix, or they have to feed it in suffix prefix, right? So which one do you put first? You put the middle is what you want to generate, but do you put the ending, the last 50 lines of the code file first, or do you put the first 50 lines of the code file first, assuming you want to generate in between? So they ablated that to see which one does best. And you can see here results on the effective infilling training here. So we can click on that, section 3.2. And Codellama without LCFT. What is LCFT? Pass at 1, at 10, at 100. So here, these are in the human eval benchmark, right, where you're doing these little coding problems. Pass at 1 means that you asked it that question and it gave you the answer, and it only had one shot. It had to give you the right answer. Pass at 10 means that it can give you 10 answers, and then if the answer is in those top 10, or in these 10, then you're correct, right? Pass at 100 means you have 100 tries to get the answer. So that's why the score here is way lower than the score here, right? So it's much harder to get it right on the first time than it is to get it right in 100 times. Okay, but we were trying to figure out what LCFT is. What is LCFT? LCFT. Here it is. Long context fine-tuning. Okay, so fine-tuning on longer context chunks of code, which is, I guess, where they did that suffix prefix suffix ablation, but I'm not actually seeing the ablation here. With and without infilling objective. Okay, so it doesn't really seem to make much of a difference here. These numbers are kind of the same. 33.6, 33.2, 36.2, 36.8. Yeah, these are kind of insignificant, to be honest. It doesn't seem to make a difference. So what you wouldn't have wanted to see is you wouldn't have wanted to see a huge negative here, right? So it could have been the case that by fine-tuning on this long context, you lose your ability to perform on these little kind of like mini sets like this, these little mini tasks, right? A lot of times in machine learning, you have this problem of transfer learning. It's sometimes called the catastrophic forgetting, where basically you train on one thing, and then you start training on something that's a little bit different, and you start to get worse at the thing that you were originally training on, right? So that's called catastrophic forgetting. And here they're kind of just showing to you, it's a little proof that, hey, even though we're doing additional fine-tuning on this long context stuff and this infilling, which is kind of longer context, it's not losing its ability to solve these little coding challenges of human eval and MBPP. So it's not hurting it. Okay. To limit the distribution shift between autoregressive and infilling training, we suppress the implicit leading space. Okay. Long context fine-tuning. Effective handling of long sequences is a major topic of research in transformer-based language modeling. Here's the original Vaswamy Transformer Attention is All You Need paper. This paper is absolutely monstrous in its amount of citations. The fundamental modeling challenges are extrapolation, i.e. operating on sequence lengths beyond those seen at training time. Yeah, so if you train at a specific sequence length, it's generally going to be good at that sequence length, right? And if it can't kind of transfer to longer sequence length. There's kind of like a problem there of like what you the type of context and sequence length that you train it on is going to be the type of context and sequence length that it performs well on. And the quadratic complexity of attention passes. So maybe another thing there, attention map. So these transformer, here, this one. These transformer, maybe not this one. I'm just trying to show you why it's quadratic. I know you guys have seen this a million times, but I'm just trying to be exhaustive here. There we go. So let's say you had a sentence here. It requires an enormous amount of resources to achieve high scores. What a self-attention map is doing inside a transformer block. So this is what a transformer block looks like. You have this multi-head self-attention here, and then on the decoder side, it's a masked multi-head attention, and then you have this cross-attention here once you have the encoder stuff coming into this decoder. But what they're referring to here with a quadratic complexity is because quadratic, right? Quadratic is square, quadrado is square, and the square comes from the fact that you have this square that is created here. Where is it? I literally just had it. Yeah, but anyways, you're creating a square. So you have your sentence here on the x-axis, and you have your sentence here on the y-axis, and the longer your sentence is, the area, which is basically going to be how much memory you need, is going to increase quadratically with the size of that. So that's the reason why context length is such a sticking point, because we just don't have enough memory to deal with it yet. Containerize all the things, QEMU with GPU pass-through to a VM specialized for NVIDIA Dockers with modularized virtual EMs. Yeah, I use containers a lot, I do use Docker containers, but the problem is that even with Docker containers, you do need to have all the NVIDIA stuff installed. So you need NVIDIA Docker to run NVIDIA Docker containers, or Docker containers that access the NVIDIA stuff. So it's like you don't run away from the problem by doing that, unfortunately. Okay, but we're looking at long context fine-tuning in which models are presented with sequences of 16,000 tokens up from the 4,000 tokens for Llama 2. So this is their long context is 16,000 tokens. Let's use the blue. Initial code. By limiting the training time spent on processing long sequences to a fine-tuning stage, we gain long-range capabilities without significantly increasing the cost of training our models. Okay, so kind of an interesting kind of justification here. So their reason for training on the small context and then fine-tuning on the larger context is literally just comes down to training cost, where it's actually cheaper to do it. Our strategy is similar to the recently proposed fine-tuning by position interpolation, and we confirm the importance of modifying the rotation frequencies of the rotary position embedding used in Llama 2 foundation models. So if we go back to our here. Yeah, back to our thing here. Look at our rotary positions. Look at this screw, right? When we're doing, nice. When we're doing interpolation, right, you can think of each token has some position embedding, which represents some point on this kind of corkscrew. When you're doing interpolating, you're basically just increasing the density of the points along that corkscrew, but it's still kind of the same fundamental corkscrew. Instead of downscaling frequencies linearly, as Chen et al. Said, so the frequencies, you could think of that as roughly kind of like how many times are you going through this little corkscrew, how tight are those little loops together, right? We change the base period for which they are derived. Specifically with rotary embeddings, the query and key vectors xn, so query and key vectors are the key parts of the attention mechanism. So I had this nice KV cache, this here. So this is the same YouTuber that I just kind of like randomly discovered this morning, but I loved this kind of visual explanation of like what the key and the values are, right? So these are the key parts of the attention mechanism. So the attention mechanism, you have your queries, your keys, and your value. X is your input. So this is your input sentence, and then you have these weight matrices, WQ, WK, WV. The key and the values are cached because they represent basically the entire sentence. So the entire sentence is largely being stored in these KVs. The query is really just this last part here, right? So when you're doing this attention mechanism, you're saying, okay, this last part that I have times the keys, which is all the information that I have currently, right? Previous context. That's going to give me a bunch of dot products, which is going to give me this attention map, right? And then that attention map, feed it through the softmax. What the softmax does is it makes everything, squeezes everything, right? So when you do those little dot products and you do multiply the queries and the keys, you're going to get a bunch of weird values. You want all those values to become nice and clean, right? In between the numbers 0 and 1. So you're going to get a bunch of weird values, but once you put them through the softmax, they become all numbers between 0 and 1, and then all those numbers between 0 and 1 are then used as kind of weights for the V, which also represents it. Here you go, weighted sum over previous context. So all you're really doing with the Q and the K is you're determining the weights by which you're going to multiply this V, right? So you're kind of saying which are the things that are going to be important in this V. If my Q and my K, if my Q for some specific, let me go here. So if my Q for this specific, if chill and cold, like the dot product between this and this is very high, I'm going to end up with a number that's close to 1, which means that when I actually go and I find the vector there, I'm going to say, okay, it's very related to this. Multiply this row here by 1 because it's important. Versus if I go to was, the Q of chill multiplied by the column corresponding to was, probably not going to be very important there, which means that when I feed that through the softmax, it's probably going to be some number here that's close to 0. And because it's some number close to 0, it means that the value here is going to go down. So, or it's going to be smaller because you're going to be multiplying it by a number that's close to 0. So that's kind of like a rough idea of what's going on there. Wow, you guys are blown up here. Big initial investment of time, but it makes everything to worry about breaking everything with an update. Okay, Paul, I will take your recommendations on containerization to heart. Instead of downscaling frequencies, change the base period. Query and key vectors n at position n are subject to linear transformation r. So here's the rotation, right, from the other paper here, or the other video of this guy, right? You can think of the rotation of just these vectors. You're rotating the individual vectors. That's what this rope is doing. So R theta dn is a block of diagonal matrix with entries of the form this. Cosine n theta I minus sine n theta I. N is the position, right? So position within the sequence. And then theta is your theta parameter. D denotes the embedding dimension. Rotation frequencies are computed as theta I equals theta negative 2I over D. And we increase the base period theta from 10,000 to 1 million for fine tuning. I think this is another thing that people pointed out. So inside this link tree that I have, someone also noted this. This is actually, I think, one of the original authors, but he kind of pointed this out. Fine-tune on sequences of 16s, increased rope theta parameter, right? So this theta here, which ultimately basically determines this frequency. Or not frequency, but the base period. And that's how they get this longer context, allowing them to gain long sequence processing capabilities at low cost. Codellama can extrapolate. All right. So they fucked with this little theta parameter here in the rotary position embeddings, which is the little extra positional information that you're adding to every single one of your tokens, and that is what allows you to increase the context length from 4,000 to 16,000. This increase allows for processing much longer sequences and reduced bias towards short distance attention. Our experiments confirm that Codellama models are not only effective with the increased sequence length during fine-tuning, but further show extrapolation capabilities and exhibit stable behavior on very long sequences. Here we go. Let's see if we actually see a little plot here. Multilingual human eval, that's probably not. Here, this is the actual plot. So context length times 10 to the 3. So this is the total amount of context length, right? 100,000 versus 20,000 versus most models are here around like 4,000, 8,000 context length. Perplexity is kind of an idea of like how good is your predictions is kind of the best way to think about it. But basically these language models are creating, right? They have their little dictionary of tokens, and then you're asking them at every single time, what is this next token? What is this next token? What is this next token? And they're telling you, okay, well, this next token, here's the probability distribution on all of the words in my dictionary for what that token is. So that probability distribution, you can then say, okay, well, over the course of this sentence, how confident was I about all of these words that I picked for every single next token? And that's kind of roughly what Perplexity is doing, is it's basically saying, how good is this probability distribution that I'm modeling over all the tokens for the next token over a whole sentence? And you can see here how it's high and then it kind of goes down over here. So it gets kind of worse. Perplexity on large source files from the validation data on the code dataset. The dashed line marks fine-tuning context length. Perplexity decreases for up to 100K tokens for all Codellama sizes. And here they have synthetic key retrieval task with a context of 16K tokens. So this is probably synthetic key retrieval task. What they probably are doing here is they probably create some fake piece of context that is 16,000 tokens long, and inside that giant fake 16K token thing, they have one key, right? So they have like a secret answer, and then they say, okay, well, this 16K context, is it actually getting all of that, or is it just thinks it gets all of it, right? So by putting that little secret key inside this giant synthetic 16K context, they can then say, okay, well, what's the answer to that secret key question? And here you're saying, okay, well, gets it 100% of the time, I guess is what it's saying. So GPT 3.5 Turbo 16K gets it pretty much 100% of the time here. This plot is kind of nonsense, though. It's basically showing you that all of them are 100%. The only one that is not getting it is the 7B model, which is the smallest model, with a relative position of key function here. So if you put the secret key at the very, very beginning of the 16K tokens and then ask Codellama 7B at the very, very end, what was that secret key? It only gets it right 50% of the time. But pretty much all of these, you can see how, especially at the end, if the secret key is the very last thing, every single one of them gets it right. If the secret key is towards the end of the 16,000 tokens, pretty much always gets it right. So it's only near the beginning, if you put the little secret key there, that some of them get them wrong. But I think what they're trying to flex here is that it's better than the GPT 3.5 Turbo. So GPT 3.5 Turbo is this red line, so you can see how it's underneath their lines, the lines that represent the three model sizes. Okay. Next thing, let's go into instruction fine-tuning. Our instruction fine-tuned models, Codellama Instruct, are based on Codellama and trained to answer questions appropriately. They are trained on 3 different types of data. We use the instruction tuning dataset collected for Llama 2 and described in detail. We use the version referred to in their paper as RLHF v5, so reinforcement learning from human feedback. This is where you're using a bunch of humans, which is kind of creepy because a lot of these humans are actually from these like low cost of living areas. So you just have a bunch of humans that are sitting there looking at the outputs of an LLM and determining whether or not they're safe. It's kind of a weird, creepy way of creating these instruction tuning data sets. Combines thousands of human fine-tuning and millions of rejection sampling examples. Each example consists of a multi-turn dialogue between a user and an assistant. The output was selected amongst several generations using a reward model. The final dataset contains both helpfulness and safety. So this is like kind of two somewhat competing ways to measure language models. We saw this in some of the other language model papers where basically helpfulness is the language model answering your question, and then safety is the language model giving you answers for potentially unsafe questions. And those two are kind of competing a lot of times, right? A model that is very helpful can be unsafe, and a model that is very safe can sometimes be unhelpful. Our proprietary dataset consists of few examples of code-related tasks. Collecting supervised data from human annotators or training from human feedback is expensive for coding. Tasks as it requires input from professional developers. Instead of human feedback, we use execution feedback to select data to train our instruction model. Interesting. So they're actually running the code, and then when you run the code, if it actually does well, then that was a good generation. And this is some of the like earliest work on kind of code problem solving with language models did this. I forget exactly what it was called, but I remember seeing this where they would basically just generate 100 answers to like a little leak code problem and then run every single one of them through an actual running Python runtime and then see which ones were actually getting the right answer. So here it's generating 62,000 interview-style programming questions by prompting Llama 270B. So you can literally ask it. It's generating its own data set here. Deduplicate the set of questions by removing exact duplicates. See, I would argue that these are way more duplicated than you think they are. Exact duplicates is one thing, but interview style programming questions have a kind of a limited set of answers, right? There's kind of like a dozen kind of high level patterns, such as a breadth first search or a depth first search, and you're kind of or a tree or something like that, and you're basically just replicating that pattern across a bunch of different questions. And usually the first thing you do when you're given these kind of interview programming questions is try to figure out what type of pattern is this. And then once you kind of know which of the 12 patterns it is, then you can just basically very easily write it. So even though you have 62,000 generated questions here, it's really just the same concept 62,000 times. Generate unit tests by prompting Codellama. Generate 10 Python solutions by prompting Codellama 7b, and then run the unit tests on the 10 solutions. Add the first solution that passes the test to the self-instruct dataset. Why don't we ask this? Here, let's do this. Let's do new chat. Oh, generate a interview style programming question for me. That is relatively easy. String reversal and capitalization. Write a function called reverse and capitalize that takes in a string and returns a new string where the original string is reversed. And, okay, so this is like kind of a little bit stupid easy, but let's see. We can take that. See if Llama 13b chat can do this. Let me do retry or undo, clear. Oh my God, it's going. Let's refresh. Put it in here. Submit. Here's a possible implementation. It's literally just one line. So here they're going backwards. So here you're treating the S as a list of characters, and in Python, a string is really just a list of characters, and you're reversing it. That's what this -1 does, and then you're .capitalize. Let's see if this answer is good. Can I copy this entire answer? Is this answer good? Should say yes. Yes, it's good and concise. Nice. Okay, so basically that's what they were doing here. All right, they're just generating questions and then filtering them with the ones that can actually run the unit tests. In order to prevent the model from regressing, is also trained with a small proportion of data from the code dataset and our natural language dataset. So here's your percentages. At least we're getting a little bit of idea of the mix, right? We have a little bit more of like, okay, this is how much code versus natural language there is inside the data, but it'd be so much better if we could actually get the dataset, you know, if they actually posted the dataset. But if they posted the dataset, then you could just train the model. So it's kind of existential for them to not post the dataset. Okay. Our optimizer is Atom W. This is a very common optimizer. It's based on this momentum. You have these extra parameters here. We use a cosine schedule with 1,000 warm-up steps. Cosine schedule changes the learning rate, cosine learning rate. So here's what a little cosine schedule looks like, right? Kind of goes up and down. So the learning rate is going down and then back up and then down and then back up. And if you're thinking of the process of training a neural net as kind of moving a marble along this hilly landscape, right, you can see how sometimes you'll get stuck in a little local minima, right? Sometimes your little marble's traveling and it kind of gets stuck somewhere. And if you have just a decreasing learning rate, it can kind of get stuck in here and it never has enough of a big learning rate step to kind of get out of this little local minima. So cosine learning rate schedules, my intuition as to why they even work is because basically they occasionally get big and they give you a bigger learning rate just for a little bit, just so you can maybe step outside of a little ditch that you've fallen into. So that's my intuition on cosine learning rate schedules. What else? 1,000 warm-up steps. So warm-up steps are steps where you're feeding the data through your model, but you're not actually changing the weights. You're not actually taking gradient steps. You're basically just warming up the momentum parameters inside your optimizer and any other kind of normalization parameters that you might have in like a layer norm or something like that. Set the final learning rate to be 1/30th of the peak learning rate. Okay. This is kind of interesting. Maybe this is, I kind of try to read into the hyperparameters for these, but they're not necessarily going to be indicative of the hyperparameters you would want to use locally, right? Because this is the hyperparameters that they're using for these giant distributed training runs on a huge amount of GPUs, and you're probably not going to have that amount of GPUs or be doing that kind of training at home. A batch size of 4 million tokens, which are presented as sequences of 4,096 tokens each. Despite the standard practice of using lower learning rates and fine-tuning than in pre-training stages, this is something that I recommend all the time. And the way that I see it is that if you use a big learning rate when you're fine-tuning, you're kind of just overwriting everything that you did in pre-training, right? So in pre-training, the learning rate is also going down, right? So over time, your ball is becoming more and more kind of slow. It's just like getting into this little local minima, and then it's just kind of like hovering there. So the last part of the pre-training, it's kind of moved very little, right? It's very finely adjusted, the weights of that neural net. So if you then go and you fine-tune and you just use this massive learning rate, you're just going to immediately just it's just gone. Now it's in a totally different part of this hilly landscape, and you might have just wasted all that pre-training juiciness, right? So in general, you want lower learning rates for fine-tuning than you do in pre-training, but that is starting to become less and less important as we become more intricate and complicated in our kind of curriculum, right? So it's no longer pre-training, fine-tuning, and that's it. Now you have pre-training, pre-training, fine-tuning, fine-tuning. There's like 10 different steps now. So now you're going to have to be thinking about, okay, well, do I want it to mostly forget here? Do I want this step to be more important than this step, right? Changing the neuroplasticity, right, if you want to use the brain as an analogy, depending on where you are in this training pipeline and how important that particular part of the training pipeline is to the final performance that you're going to be measuring. We obtain the best results while retraining the original learning rate of the Llama 2 base model. We carry these findings to the 13B and 34B and set their learning rates to 3e to the negative 4 and 1.5e to the negative 4. This is kind of becoming a meme, this learning rate here, 3e to the negative 4. People love it for some reason. For Python fine-tuning, we set the initial learning rate to 1e to the negative 4 instead. Okay, so you can see here how at least for the fine-tuning with the Python, they're making it a little bit smaller. So if we actually go back up to this part here, 3e to the negative 4, 3e to the negative 4, and then they tune it down here. So 1e to the negative, or 3e to the negative 4, 1e to the negative 4, so smaller. So you don't want this Python code training to just overwrite everything that you did here, right? So you kind of decrease the learning rate as you go down this training pipeline. We train it with a batch size of 524,000 tokens on approximately 5 billion tokens in general. For long context fine-tuning, we use a learning rate of 2e to the negative 5. So see here, now they're making an even lower learning rate. A sequence length of 16,000 and reset the rope frequencies with a base value of theta equals 10 to the 6. Right, so this is the theta parameter that they were changing, which changes kind of that spiral, which is being used inside the rope position embedding, which is rotary position embeddings. The batch size is set to 2 million tokens for model sizes 7B, 13B, and 1 million tokens for the size 34B. Training lasts for 10,000 gradient steps. We observed instabilities in downstream performance for certain configurations, and hence the number of gradient steps to 11,000 for 34B and 3,000 for Codellama. So this is kind of sketchy, right? And this is one of the things that I noticed as well when doing a little bit of research for this, is that there seems to be competing objectives, right? Long context fine-tuning can hurt short context results, and infilling can slightly degrade benchmarks too. So I know that we looked at a graph earlier that said it doesn't matter, but it does seem like it does matter a little bit, where if you long context fine-tune for a little bit too long, it starts to perform worse at these short context tasks. So there is a little bit of a domain gap between long context and short context. But I don't know, if you take a step backwards from all of that, I feel like that's all noise, because eventually once the GPUs are 100 times bigger, and once our data sets are 100 times bigger, and once our compute is 100 times bigger, it's not going to matter. This like long context, short context, do I fine tune on the long context and then instruction like all of that is going to go away, because the model, you're just going to feed every single piece of data into the biggest possible model with the largest possible context, and it'll just work better than anything else. Codellama pass at scores. So here they're comparing against a bunch of other models. So you have GPT 3.5, GPT 4. GPT 4 has kind of remained at the top for pretty much everything. So Codellama, instruct, unnatural code. What the fuck is unnatural Codellama? Pass at 1 scores are computed with greedy decoding. Pass at computed nucleus sampling. Blah, blah, blah. Models are evaluated 0 shot. Where is unnatural Codellama? What is that? Okay, but Codellama 34B, I think this is probably the strongest. So 48% at pass at 1 compared to 67%. So GPT-4 is still wiping the floor here with an extremely strong model. Right, but like, look at this. We don't know anything. You don't know what any of these scores are because you can't actually even evaluate GPT-4 on any benchmark. Don't even know what size it is. Here you're comparing StarCoder. We actually reviewed StarCoder on this channel as well. Whenever we reviewed it, it actually seemed really poor. It was actually quite shitty. So 48%, 40%. Some of these numbers are not necessarily indicative of how good they actually are. What is this one? Control F, unnatural. Let's see. For comparison purposes, we also fine-tuned a Codellama Python 34B on 1,500 unnatural instructions similar to Honovich using the same prompts for the self-instruct. We do not release this model, but we observe clear improvements. What is this? What is this? Unnatural instructions. Let's search that up. Let's search this up. Unnatural instructions. Large LLM. This one. 2022 paper, Honovich, PDF. Oh, okay, so it's also meta. Did we read this? Maybe we read this. Let's see. Instruction tuning, blah, blah, blah. Approaches rely on vast amounts of human data. In this work, we introduce unnatural instructions, a large data set of creative and diverse instructions collected with virtually no human labor. We collect 64,000 examples by prompting a language model with 3 seed examples of instructions and eliciting a fourth. Okay, so this is more of kind of the synthetically generated prompts, which is a pattern that you're seeing more and more. We read another paper last week where basically you're generating text data synthetically. You're using a language model to generate either the entire prompt and answer, or maybe just the prompt and then the answer, or just the instructions. Just basically more and more of the data that these language models are trained on is being itself generated from language models. So you're seeing this kind of move into synthetic data as the core data that is being used for training. And some people call this data augmentation, but I don't know. I'm a bit of a synthetic data enthusiast myself, so I see that as a overall good thing, because synthetic data is much cheaper and much more accessible to everyone. So if we can get to the point where you can train entirely on synthetic data, then that means that data sets are no longer a moat, right? So right now, a lot of these companies, the moat that they're using is just their data set. They have a bunch of data that they've cleaned, and we're seeing more and more that you can generate data from a foundation model and use that to train your own model. And if you can train your own model, then you don't need to rely on these guys. Synthesizing is all you need. Yeah. Okay. I'm starting to get a little concerned that the Twitter streams are going to die out here. Okay, it still seems like it's going. Okay. Because I know that I like to stream kind of longer, but if I stream too long, I might get kicked off some of these sites. After 100k tokens, the perplexity increases only slightly. Okay, we actually did see this chart already. Infilling models reach state-of-the-art performance in code infilling among models of their size. We evaluate on 2 related coding infilling benchmarks based on the human eval benchmark. Human eval turns reference solutions of the human eval into infilling problems by masking out either individual lines or blocks. So here's your infilling. Our models outperform all other infilling models of their size. How many other infilling models of their size are there, though? So the results in random span are significantly worse in suffix-prefix middle than in prefix-suffix middle format. So you're trying to generate the middle, right? And then you have some amount of code on top and then some amount of code below. So suffix-prefix means that you give it the lower part first, then you give it the upper part, and then it generates the middle. And that's actually worse than if you do the beginning, then the end, and then you ask it to generate the middle, which kind of makes sense, right? You could guess that if position embeddings and the context length was an issue, then you would probably want suffix, prefix, middle, because you would want the prefix as close to the middle as possible. But because we know that the context is quite good, these position embeddings are quite good, it can it still knows what's happening 16,000 tokens ago, then prefix, suffix, middle is better because the prefix gives you the information you need in order to understand the suffix. So I don't know, I'm just kind of speculating there. This is all a black box. I have no idea why suffix, prefix, middle works better than prefix, suffix, middle. We have not implemented this. Translates the human eval infilling benchmark to other programming languages using multiple E. Single lines are masked, predictions are scored. Outperform all open infilling models across 3 programming languages. Okay. Here we have finally the comparison of prefix, suffix, middle versus suffix, prefix, middle. I mean, here you don't know because encoder, Santa coder, and star coder don't have the prefix, suffix, middle. You can only do suffix, prefix, middle, I guess, but actually it's really not that much of a difference. You're talking about like maybe a couple percents here, 67, 72, 74, 77, so it's not hugely important. And it's actually more interesting that there's more difference in Python, right? So Python is kind of like a scripting language, but more often than not, a Python is more of a script, right? So it's like you run this thing, then 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 you run this thing, right? It's like that's the way that Python kind of works, right? It has this kind of global interpreter lock. It's like going down your thing one by one. So it would make sense that the difference between prefix, suffix, middle, and suffix, prefix, middle is more important in Python than it is in Java, right? If you think about what type of Java code is this training on, that type of Java code probably is more just like little individual functions that are, you could kind of reorder them and it still makes sense, versus in Python, maybe it's just a bunch of scripts, and if you reorder the stuff in the Python scripts, you're fucked, right? Because it's like the ordering is very important. So it makes sense that maybe the gap here is 5% for Python and only 3% for Java. But then that doesn't make any sense for JavaScript, but I don't know. I don't write very much Java or JavaScript, so maybe somebody on the comments is a Java or JavaScript connoisseur, and they can make sense of this here. Why is JavaScript less important than Java when it comes to the ordering of the prefix and the suffix? Here's the little key retrieval task that they were saying, where they basically insert a special secret key, and then they try to get the model to basically, did it remember that secret key? Single line completion, average single line completion performance. Bleu is a language model benchmark. I don't know, these numbers seem pretty standard here. Performance on short context, ablation studies. Fine-tuning Llama 2 versus training from scratch on code. The fact that you can transfer learn from the base Llama 2 model, I think, is just more evidence to the fact that we're moving into a world where the giant AGI is going to be just trained on everything. Instruction fine-tuning. Compare it to Llama 2 for coding tasks and helpfulness. Here's your perplexity. This is actually going down, so this actually shows you that they could have kept training. You know, oftentimes it kind of goes like this, and it flattens out, and that tells you that you're kind of getting to a point where you've extracted all the juice that there is out of that data set, but these curves for these language models, they kind of just show you that you could just keep training these and they would just keep getting better and better. Further training would be beneficial. Results are presented without infilling. So this is the from scratch model, and this is the one that is initialized from the Llama 270B kind of generic text model, and you can just see already that gap there. And it's not like it closes, right? So it's not like this blue line catches up to this orange line. It's just perfect, like they continue to be like this. So transfer learning in language models works. Impact of self-instruct data. The scores are computed using greedy decoding. Self-instruct. Oh, this is exactly what I wanted to see. Or maybe not. It's the opposite. This is saying that self-instruct helps it. Self-instruct gives you a 42 score and a 40% score. Doesn't seem to affect MBPP, but I would say that this is because human eval is kind of a chat kind of problem anyways, right? It's like human eval is kind of more akin to like a chat conversation, because these are little coding problems, than like actual real life coding. I would say that if you were actually doing like infill coding in a real code base, I would think that self-instruction data would actually negatively affect the performance. But here we only see performance on human eval and MBPP, which are kind of like contrived tasks anyways, so. Value of self-instruct data. To perform ablations following the value of self-instruct, we generate with our own model. We evaluate the capacity of the model to answer questions. We use a zero-shot version. Prompt the model to generate the code between this and this. So here are the tokens, probably the special tokens that they introduced, where it's like fill in this part right here in between this token and this token. Human eval code Llama 7B, 13B, and 34B, so the three different sizes. Pass at 1, at 10, and at 100. So pass at 1 is the hardest. That's why it has the lowest score here. You can see here different temperatures. Temperatures change. Here, I'm gonna bring it up. I know you guys have seen this before. Temperature LLM explained. But I just love this No, it's not this one. This one? No. LM settings, temperature. Oh my God, they've already polluted. The SEO is gone. I don't remember what the name of this thing was anymore. Was it this one? All right, there used to be this very nice, pretty GIF that I would show that shows you how changing the temperature. Yeah, this thing here. So when you change the temperature, you kind of change the output over each of the tokens, right? The language model is picking the best token for each spot. So it's saying, at this spot here, what's the next token? What's the next token? What's the next token? And here you have a probability distribution over 10 classes, but in a language model, there's thousands of possible tokens, so it's like a probability distribution over thousands of tokens. Whenever you increase the temperature, you're basically making all of the probabilities here just a little bit closer, a little bit more squashed, so that, yeah, right here. So you see how this temperature is going up. Now, rather than the next token obviously being this number 9 here, maybe it kind of is not as obvious as a choice anymore, right? Which means that the next token might be something else. Maybe it's this 0, maybe it's this 4, right? And if you, that kind of explains the behavior of when you jack up the temperature in a language model, you get kind of more randomness. And it's because the probability of the best token compared to the other tokens becomes less and less exaggerated. So that's temperature. What else? Codellama scores different temperature values. Results are presented. So I don't know. I guess if you make the temperature higher, it's going to be more random. Therefore, the score is going to be lower. But actually interesting here. So if you increase the temperature, if you're evaluating with a pass at 1, of course it's going to be lower, right? Because you're going to be more random. But if you increase the temperature and you're evaluating with pass at 100, you actually start getting way higher scores because the 100 answers that you generate are more random, which means they're more likely to have the right answer. So this is kind of like a weird situation here where depending on how you're evaluating your language model, having a higher temperature is actually better. So you could kind of think about what this would look like in an IDE, right? Do you want your IDE to have a very big model and it just has a very low temperature and it evaluates that big model with a low temperature once? Or do you want an IDE that has a very small model that runs at a very high temperature and it generates 100 answers for everything that you want and then it picks the best one for you, right? So that's kind of cool. Look at that. That's the 34B model with a very low temperature would give you a pass at 1 of about 0.45 versus the tiniest model at a higher temperature would give you a pass at 100 at 0.85. So here what you're actually seeing is that if you have a way to filter these 100 generated answers, you're better off with the small model high temperature than you are with the big model low temperature. So that definitely has implications around the way you're going to be using these models for products. Responsible and safety. Okay, we're just going to skip all of this responsibility and safety crap. I just don't care. Safety, reward, scores, distribution of red teaming. Okay, guys, it's super safe. Don't worry about us. We're super safe. It's all good. Okay, we got related work. Open source, closed source. Landscape is marked by whether the technology is free and the code is available for research and commercial use. All right, ChatGPT and GPT-4, Palm, Chinchilla are closed source, while Bloom, OPT, and the seminal work of Llama are public. The more recent Llama 2 has been released under a custom license. A similar dichotomy exists for code models, being closed source, whereas recent Santa Coder have been open source and allow for commercial use. In this work, we allow for commercial use of the models under the same terms. Moreover, our largest model is significantly larger than previous open source models. I don't know. I guess they don't really say anything. They just kind of shit on GPT a little bit for not being open, but then they themselves are not necessarily open either. Meta is the most open of the big tech companies, significantly more so. They release papers, they release their code, they release these models. You can use them for commercial use, which is big, but they're still not fully open. I would want to see the data set. That's one thing. I would want not this weird commercial license that you have to be kind of checking your back. I would want something that was literally just MIT license, Apache license. Give me a license that I understand, not some weird shit where I'm getting afraid of being sued. Data. It is well known that data quality is critical. Also true for code. Modern models are trained on publicly available open source code. In addition, Alamanis and Alal discuss the impact of effective deduplication selecting code based on their number of GitHub stars. Oh, shit. So, that's kind of interesting. The code that they're using is based on GitHub stars. So, they don't... If your little personal project, if you paid someone to... if you paid one of these sketchy services that gives you GitHub stars, maybe your shitty personal project is being trained on because they mistakenly think that stars are popularity, but stars are misleading. Filter data up to containing textbook quality code and add synthetic problems collected using GPT 3.5. In order to obtain good performance on simple benchmarks, we follow the approach of learning from publicly available code only without additional meta-level or temporal information such as issues or commits. We also do not train our foundation model on additional synthetic exercises since we do not want to take the risk of reducing the scope by simple coding exercises. So they're aware of the fact that if too much of your training corpus is these kind of coding exercises, then the model kind of becomes very narrow and really isn't going to perform well in real code bases outside of these little coding exercises, which is important because that means that they weren't just trying to beat GPT-4 on human eval and MPPP, right? One way that they could have approached this Codellama project is they could have said, okay, well, we really want to have the highest possible score on human eval and MPPP, and at that point, let's just really try to make our data set as similar as possible to these simple coding exercises benchmarks. But I think they realized that actually getting the highest value on human eval and MPPP is really not as important as releasing a code model that actually people are going to use in their production code bases. So let's not try to overfit to just to beat this benchmark. So that's good of them to do that. Code understanding and synthesis. Code summarization, refinement, translation, fixing bugs, fixing errors, generating unit tests, solving math problems. So I guess this is there's a whole bunch of problems around just code synthesis. Program synthesis. So here they really only want to focus on actually writing code and not what is the bash command for X. Additional modifications to LLM training and inference. The number of works proposed incorporate within the training objective, which specialize objectives for code. Contrastive learning through semantic preserving code transformation. Leveraging abstract syntax trees to learn tree-aware positional encodings. Okay, so your positional encodings that they're using here are based on just there's a paragraph, a sequence of text, and the ordering of every single word in that text is basically one to the end, right? There's this kind of if you're reading a book, that's what the kind of positional encodings right now are based on, where it's just everything is in this book and it's kind of token by token. But code isn't like that, right? In a code, you might have a file in which there's a bunch of functions that are defined, but if those functions were reordered, it would still be the same exact file with the same exact functionality. So here they're saying, okay, well, maybe our positional encodings should be more clever to account for that, right? We shouldn't just say, hey, this is the positional encoding of the first function because it comes first in this file, and the second one because it comes second, and the third one because it comes third, right? that doesn't matter. So can we come up with some special way of encoding the position of each of the tokens in those functions that is more incorporating information about how the fact that each of those functions are separate and they can be basically reordered rather than just taking the literal position of the token in the entire file? That's kind of a clever idea. I like that. A recent stream of work takes into account program execution or unit tests to filter, cluster, or improve the correctness of programs. This is what we saw with the pass at 100, where this kind of filtering might be the way to go. Guessing a lot and then filtering rather than just guessing correctly on the first time. Improving the base model rather than tweaking the inference. Nonetheless, interesting direction. Long sequences. Scaling transformers and LLMs to long input sequences has attracted much recent interest. The context length supported by available models has seen a steady increase. 8K token sequences. We do not rely on handcrafted sparsity patterns such as those proposed by Guo, who operate on sequences up to 4,000. Modify the encodings of positions instead. So the Llama pre-trained Llama 2 models utilize rope, which is what they're using here, and all they're doing is they're changing the rope hyperparameter theta for a simple modification which does not require any architectural changes or restrictions. Yeah, if you changed any of the architecture of the original pre-trained Llama 2 model, then you wouldn't be able to transfer from that, right? So if they wanted to do something completely different, if they wanted to try a different architecture, they would have to train it from scratch. But in this case, they really wanted to be able to just take that pre-trained Llama 2 model and then train it on code, fine-tune it on code, even though it's kind of more of a multi-step process. But that's why they couldn't really change the architecture of the Llama 2 model. They had to just use it as is. All right, finally, we're almost at the end here. Discussion. We're going to time it perfectly to 2 hours. We release a family of code-specialized Llama 2 models called Codellama with 3 main variants, 7B, 13B, and 34B. With the real-world applications, we trained our 7B and 13B models to support infilling, and all of our models to leverage large contexts. We tested their stability and inference up to 100K tokens. Large context fine-tuning and infilling come at a cost on standard benchmarks, left-to-right code generation benchmarks, that are all based on short sequences. Yeah, I kind of agree that all these benchmarks are just not necessarily predictive of performance on true, like, production code, you know? I think these benchmarks are just these little, like, leak code problems, and much like leak code problems aren't actually useful for determining the quality of an engineer, I think leak code problems are not a good benchmark for code language models. Our 30B model is a state-of-the-art amongst public models on standard Python completion, and all other models are competitive compared to the models with similar numbers. On multilingual benchmarks, even our smallest model outperforms every other public model. The Codellama Instruct models are trained to provide zero-shot instruction ability to Codellama. In this further fine-tuning, we also somewhat distillate Llama 2 chat. This is a made-up word. It should be distill. We focused not only on being more directly helpful, but also sought to provide a safer model. Okay. So that's the paper. We can scroll down to the appendices here. Let's see if there's anything interesting. Acknowledgements. More multilingual. Zero shot. There was one picture that I wanted to look at. It's the picture in the thumbnail. I don't know if we passed it or not. So you have some examples here. Let's go back up. I think we might have skipped it. Let's get it. Come on, this one. Boom. This is the picture that I wanted. Okay. So let's explain this figure right here. So in this figure, we have the 3 different sizes, 7B, 13B, and 34B. So these 3 different sizes, we have correlations between languages. Correlation scores between the Python, C++, Java, PHP, C#, TypeScript, and Bash reported for different model sizes. The code for this figure was generated with Codellama Instruct. Nice that they tell us that they actually generated this entire figure with Codellama Instruct. But the reason I found this interesting is that the small model doesn't have a very high correlation between languages. So you see this? You see these languages are all kind of unrelated, which means it's treating these differently. It has a different part of the model that's doing the C#, a different part of the model that's doing the Python, right? It's kind of like, it's almost keeping them separate inside the model. And when I say different part of the model, I don't mean like an explicitly different part of the model. I mean like within the 7 billion parameters, there's kind of different paths that result in Python and C# and so on. But one thing that you're noticing here is that as the model size increases, the correlation goes higher, which means that there is some kind of higher level semantic like understanding of coding that exists at this 34B model. This 34B model, like whether or not it's programming in Python and Java and C#, it's programming, and then it just happens to pick whatever language you want. But the kind of idea of programming is kind of compressed. It's found a compression of like all code into some kind of higher level abstraction. So one thing that we talk about on our Discord community all the time is this idea of like intelligence is compression, right? So the fact that here the 7B model just keeps these things a little bit more separate, and this 34B model kind of like mixes them all together, to me means that it's found some higher level abstraction, some kind of coding language that is all coding languages. I feel like I explained that kind of perfectly, but I find this very beautiful because it means to me that all programming languages are really the same programming language, and that's what this 34 billion parameter model has figured out, versus the 7B parameter model. All programming languages are not all the same, and they're all kind of different. Yeah, the emergence of logic. Right, and actually, here's the next thing, right? So imagine this plot, but rather than Python, C++, Java, PHP, TS, rather than that, imagine each of these columns being coding, medical, chemistry, biology, physics, right? Right now, we're still working in this world where we're like kind of separating all these things, and we're saying, okay, well, biology and medical stuff is very different from coding, therefore we should keep them separate. But no, I don't think that's the way it's going to work. I think it's going to eventually come this way. Once you get to bigger and bigger and bigger models, they're going to realize that all knowledge, all human knowledge, everything that any human has ever thought, every single field of study, every single possible thing you could think of is actually really just a more fundamental thing in a slightly different viewpoint. And I think that these big models, they're going to discover it. And right now we're still here. We're still at this world where we have a coding model, and we have a medical model, and we have a this model, and we're like fine-tuning these general models, these general foundation models into specific narrow domains. But I just don't think that's going to last very long. I think once you give it a couple more orders of magnitude on the data, a couple more orders of magnitude on the model size, the training time, the context length, I think they're all just going to start to converge, and you're going to get to a point where it's just one huge model that is state-of-the-art at everything. Yeah, category theory and mathematics. All right, we're just at the 2-hour mark here, so I'm going to go ahead and just summarize real quick for you guys. All right, so today we read Codellama. This is a release by Meta AI, big release, big paper. This is foundation models for coding. You can use them on websites like Hugging Face if you don't have a GPU at home. If you do have a GPU at home, you can basically download the model. You just have to sign away your kidney and sign some weird license that you don't really know what the fuck you're signing, but you sign it anyways just because you can get it to run at home. And what are these? So basically what Codellama is basically they took Llama 2 right here, which is their generic language model. Go back up, right up here. They took Llama 2, their generic code or generic language model, and then they basically trained it with this infilling task. So this infilling task is basically you have a whole file of code, and they take the bottom part of the code and they kind of put it right at the top, and then they take the bottom part and the front part, and then they ask it to fill in the middle. So it's kind of like filling in the middle of a piece of code. They train it on 500 billion tokens of that, and then they have two possible steps here. They have a bunch of different models. So in one thing. They train it only on Python, or they fine-tune it only on Python, and then they fine-tune it on long context Python, which just basically just means lots of tokens. And then they also have a more generic one, and then they also have a instruction-tuned one, which is kind of this chat conversation back and forth kind of model. So this paper is basically largely that. It's just they have Codellama, which is basically just code versions of the Llama 2, which have slightly different types of fine-tuning, and a slightly more complicated version of training pipelines here. And I think that there's a couple things that this paper at a high level to me showed, which are interesting. One is that long context and short context are potentially competing with each other a little bit, right? Where I think this might just be an artifact of the fact that short context code and long context code are different, right? Short context code is generally these kind of like leak code problems. Long context code is generally something different. So maybe that's just an artifact of just the code itself, but context matters. The context that you trained on matters. The other pattern that I saw here was this idea that curriculum is becoming more and more complex. So curriculum is, it used to be that you just had training. Then you had training and fine-tuning. Now you have pre-training, you have training, you have multiple steps of fine-tuning, you have instruction fine-tuning. So the kind of training pipeline is becoming more and more complicated. And we saw how even for the learning rate and all these different optimizer hyperparameters, you're changing these depending on where in this training pipeline you are. So like the kind of recipe for training is becoming more complicated and engineered. One thing that was maybe negative is that they didn't tell us the data set. So they kind of continued the tradition of these companies not really telling us what data set they were training on. And we have some evidence that, not this one, but someone on Twitter found that it's actually outputting usernames from Stack Overflow. So they are training on Stack Overflow, which you probably could have guessed, but they're not going to admit to that legally. And what else? They did a little hack with the Rotary position embeddings such that you can use a longer context, but they kept the Rotary position embeddings because that's what the original Llama 2 model was trained on. I could see different position embeddings becoming more like those could change, right? Rotary position embeddings are kind of like anything else in the model architecture where they can change from year to year to year. So those are probably going to be new and different ones in the future. And that was pretty much mostly it. It kind of performs it's better than all the other open source models, but it's not as good as GPT-4. GPT-4 is still the king, and that's why they keep it super secret, because they don't want anybody else to know. But, fuck them for doing that. And that's pretty much it, guys. And then I thought this was kind of cool too, where basically the larger model is finding some kind of more high-level abstraction that all code is really just the same versus this small model just keeping them a little bit more separate. So I thought this was cool as well. But that's that. Is this model released? Yeah, this model is released. You can download it if you want. And with that, I'm going to close this with a didgeridoo blast. Thanks, everybody, for listening. Thanks, Blizzard, Yujun, Salman, Ed, John, Josh, everybody.